Hi everyone! In this video we're going to start learning about the relationship between two variables. So far we worked with univariate data. This is data in which a single variable is measured for each individual in the study. For example, if individuals are very scarce, then one variable that we can choose to measure is the annual fine for parking violations for each car. Today we're going to start learning about bivariate data. This is data in which two variables are measured on an individual. For example, if individuals are the American black bears, then we can choose to measure their total length and weight. But what's interesting about bivariate data is that we analyze it. We try to determine if there is any relation between the variables. For example, does the length of a bear affect its weight or vice versa? And furthermore, if we know weight of a bear, can we predict the total length of that bear? So we're going to learn how to answer questions like that in this topic. But first, let's develop some terminology. The two variables measured by bivariate data have names. They're called explanatory variable, which is commonly denoted by variable x, and response variable, which is denoted by variable y. And the reason why these variables have such names is because as we analyze their relation, we might conclude that one variable explains or predicts the other variable. And we can express this relation mathematically using an ordered pair, something that you learned in algebra. The value of explanatory variable we would put in the first place or in the left position, and the value of the response variable we're going to put in the second or right position. So let's practice. In this exercise, we're going to try to determine which variable is explanatory and which one is response. So the first variable is the number of hours a student studies for a quiz, and the second variable, students' score in points on the quiz. So basically, we just have to ask ourselves, does it study time that affects quiz results, or quiz result affects the study time? And using the common sense, you would probably agree that the number of hours a student studies for a quiz might explain or predict student score on the quiz. So the first is the explanatory variable and the second one is the response variable. For the second example, the variables are the height in inches of a boy and the age in years of a boy. So let's think, does the height explain the age, or the age of a boy would explain or predict the height? That's the second one, right? Age of a boy is the explanatory variable, and height of a boy is the response variable. And the last example, the two variables are the number of minutes since the potato was removed from the oven, and the temperature in degrees Fahrenheit of the potato. Same type of questions. Would the number of minutes since the potato was removed from the oven would explain or predict the current temperature of potato, or the other way around? Well, in this case, the time the potato was out of the oven would affect the current temperature of the potato. So the first one is the explanatory variable and the second one is the response variable. So you got the idea, right? Next, let's talk about how we can organize bivariate data. One of the easiest and intuitive ways to organize bivariate data is by using a table. In one column, we list values of the explanatory variable, and in the second column, list the corresponding values of the response variable. But if we combine these pairs of numbers or ordered pairs from the table with a coordinate system, you probably remember this one from algebra. The coordinate system represents two perpendicular number lines. The horizontal number line would be for explanatory variable. Remember how in algebra it's called x-axis. And the vertical number line will be for the response variable. This is identical to the y-axis in algebra. So if we take a coordinate system and plot the ordered pairs as points, we're going to obtain a graph that's called a scatter diagram, sometimes also called scatter plot. So that's the graph that illustrates bivariate data. As we already said, it's interesting to determine if there is any kind of relation between the variables in bivariate data. And this kind of relation is called association. So we say that there is an association between the explanatory and response variables if the response variable changes as the explanatory variable changes. So in other words, change in one variable causes the change in the other variable. And next we're going to learn how we can categorize associations based on their shape, direction, and strength. First, let's start with the shape of an association. We're going to split associations in 3 different groups. The first one is the linear association. Another name for it is correlation. And we can visually determine linear association if the points of a scatter diagram or scatter plot lie close or on a straight line. That's where the name comes from, linear association. Another type is a nonlinear association, and the points of a scatter plot would lie close to some kind of curve that's not a straight line. But it is very important that points still follow some kind of pattern. And finally, we can have bivariate data with no association at all. So visually, if we look at the scatter plot, we're not going to be able to draw or imagine any curve that would come close to all or most points of that scatter diagram. And the type of the association that we're going to focus on study is the linear association. Next, let's talk about the direction of an association. Variables can be positively associated, so visually we'll see the increasing pattern. As the explanatory variable increases, the response variable also increases. We say that variables are negatively associated when the response variable tends to decrease as the explanatory variable increases. So visually we'll see the descending pattern of the points on the scatter diagram. And finally, there could be associations that are neither positive or negative, but these are going to be the cases when we have nonlinear association or no association at all. But for next example, let's try to identify the direction of each correlation, which is another name for linear association, without looking at the scatter diagram, but by just using the common sense. We already saw these examples and determined which variable is explanatory and which response, but now let's try to determine the direction. So for the first example, we have the number of hours a student studies for a quiz affects the student's score on that quiz. So let's think. As the explanatory variable increases, in other words, as the number of hours student studies increases, what happens to the response variable? Does it go up or down? So as the student spends more time studying for a quiz, what can we expect for student's score in that quiz? Well, we would expect, using the common sense, that the result is going to be higher, which means that the direction of this association is positive. As explanatory variable increases, the response variable also increases. Let's try with age and height. So explanatory variable is age of a boy. So in other words, we say as the boy gets older, what can we predict for a boy's height? Well, the height will go up. The boy will become taller and taller, right? Which means that this association is also positive. And finally, the last example. The explanatory variable is the number of minutes since the potato was removed from the oven. So as that time increases, as more time goes by, what happens to the response variable, the temperature? Will the temperature of the potato go up or down? So using the common sense, we know that potato will be cooling down, so temperature will be going down. So in this case, as the explanatory variable increases, the response variable tends to decrease. That's the definition of the negative association. And finally, let's talk about the third characteristic of an association, and that is its strength. Generally, we can say that association is perfect, strong, or weak. The perfect association is the one such that there exists a curve that passes through all the points of a scatter plot. The association is called strong if a curve comes quite close to all the points, and the association is called weak association if a curve comes somewhat close to all the points. But as we think about those definitions, the first one should make clear sense because we can see when curve passes through all the points of a scatter plot, but the second and third, quite close, somewhat close, those two definitions are a little vague, and there could be some disagreement on whether something is quite close or somewhat close. So we're going to use a different method of determining whether association is strong or weak. And that is by using the correlation coefficient. and that is a number that measures the strength of the association. Let's just have a brief introduction about the correlation coefficient, but we're going to talk about it in more details in the next video. So these are the properties of the correlation coefficient. First of all, the correlation coefficient is denoted by lowercase r, and its values are always between -1 and 1 inclusive, meaning that it can be -1, it can be 1, or anything in between. The next two properties basically say that correlation coefficient can be positive or negative number. And that's the mathematical way of saying that. So if r is greater than 0, meaning that it's a positive value, then the variables are positively associated. And if the correlation coefficient is a negative number, r is less than 0, then the variables are negatively associated. Let me illustrate that. Here we have scatter diagrams of two linear associations. One has the correlation coefficient 0.9, and the other one has the correlation coefficient negative 0.9. Variables for the first one are positively associated. See how we have this increasing pattern. And variables for the second one are negatively associated. You can see the decreasing pattern. Now the next property is that when the correlation coefficient r equals 0, then there is no linear association. And here's the picture illustrating a scatter plot showing no linear association, and its correlation coefficient is stated to be 0. Here's the next property. It may be at first a little confusing, but we'll try to figure it out. So it says the larger the value of, and this is absolute value of r, the stronger the linear association will be. So I can rephrase this property and say that further away r is from 0, the stronger the linear association will be. For that, I'd like you to look at this scatter plot. The correlation coefficient of this linear association is 0.6. And this scatter plot, this one has correlation coefficient 0.9. Which correlation coefficient is further away from 0? Well, 0.9, right? It's further away from 0. And as we can see, the association is stronger because points are closer to some imaginary line. So if I draw an imaginary line here, points will be closer to it compared to this scatter plot, because if I draw an imaginary line over here, points are more scattered. So further away, correlation coefficient is from 0, stronger linear association. And that's going to be true even when correlation coefficient is a negative number. Still, further away that number from 0, stronger the linear association. So positive and negative sign only tells us about whether it's positive or negative linear association, whether it has increasing pattern or decreasing pattern. That's all it is. And finally, the last property, we just said that further away the correlation coefficient is from 0, stronger their linear association will be. What if it's at 1 or -1? Well, that's when the association is the strongest, which we call the exact association. And that's when points of the scatter diagram lie exactly on a line. And these two pictures illustrate this case. So when correlation coefficient equals 1, it's exact positive linear association. It has this increasing pattern, and we can see how all points are aligned and can be put on one line. And then when correlation coefficient is -1, it's the same case as far as all points being on a line, but since we have this negative sign, that indicates that association is negative, which means that it has decreasing pattern. Okay, so far we learned that two variables in bivariate data are called explanatory and response variables. We learned that bivariate data can be organized in tables or scatter diagrams, and that the relation between the two variables is called association. We also learned that association can take different shapes, but we're going to focus on linear associations in this course. We'll learn that linear association can be positive or negative, that is direction of the association, and that the strength of an association can be effectively measured by what's called the correlation coefficient R. In the next video, we're going to learn how to compute the correlation coefficient for the given bivariate data.